So let's put it all together. Your book doesn't have a very good example for this, and so I've made up my own. We're going to graph j of x equal to 3x to the fourth plus 5x cubed minus 17x squared minus 13x plus 6. I figured the j of x was a good touch since I'm making this problem up, me, Jeff Paganini, your professor. So j of x is what we're going to go with this. All right, so I've put the higher order graphing steps to the left on our screen. And so let's talk through this step by step. Step 1. What is the end behavior? Well, I see that we have x to the fourth, and I see this is positive 3. So it tells us that the left and the right are both going to go up, which is the same as saying they're both going to positive infinity. All right, we've got that taken care of. 2, how many turning points is this thing going to have? Well, it's x to the fourth, and what we say is 1 minus that number. So the TP, the turning points, is going to equal 3. Now it could have less than 3, but at most it's going to have 3. Number 3, the y-intercept. The y-intercept, just like before, is the value that doesn't have an x with it. So in our equation here, the only one that doesn't have an x is the 6 here. And so our y-intercept is going to be 6, or as we like to say, 0, 6. That brings us to the x-intercepts. It's going to have at most 4 x-intercepts. It could have less than that, but generally speaking, it's going to have 4 x-intercepts unless there is a multiplicity factor. To find the x-intercepts, though, that's where we need to do our rational zeros theorem and synthetic division. So let's start out by doing the rational zeros theorem first to discuss what potential zeros there are. So remember, we start with the p's and q's, which tell us the potential zeros are these. Everything's plus or minus. So here we go. Let's do the p's down here. Factors of p are 1 and 6 and 2 and 3. For q, factors of 3, oh, that's great, 1 and 3. All right, so here we go. For the zeros, 1 divided by 1 is 1. 1 divided by 3 is a third. Now let's do the 2's. We've got 2 over 1, that's 2. That's not on our list, so let's put down 2. We've got 2 over 3. That's also not on our list, so we'll put that down. 3 over 1, that's not on our list, is 3. But 3 over 3, ooh, that is on our list as 1, so we're not going to repeat that one. 6 over 1 is our next value, or 6. And then we've got 6 over 3, which is the same as 2, and that's already on our list. So here's our list. We've got 1, 1/3, 2, 2/3, 3, 6. We've got 6 values here. Each one of them could be plus or minus, so that's a total of 12 values to try. So now we need to do some synthetic division to decide if 1, 1/3, 2, 2/3, 3, or 6 is our zeros here. So let's start with 1. 1 is always a great value to start with here. So let's put our 1 here and get our box set up here. So we've got 3x to the fourth. We've got 5x cubed. We've got negative 17. We've got negative 13. And we've got 6. All right, extend our bar here. Put our new bar in right there. And drop our first number, 3. 3 times 1 is 3. 5 and 3 make 8. 8 times 1 is 8. Negative 17 plus 8 is negative 9. Negative 9 times 1 is negative 9. And I can see right now that I don't need to go any further because this isn't going to check out. There's no way this negative 22 is somehow going to turn to a negative 6 to tell us that 1 is a solution. So 1's just not it. It's still a great starting spot, though. But now, let's go ahead and do negative 1. And since the number's already here, what I'm going to do is I'm going to make this negative 1 right here. I'm going to erase what we've got, and we'll start again. All right, we've got a fresh space now. As you can see, the 3 came down still, and that doesn't change. 3 times negative 1 is going to be negative 3. 5 and negative 3 makes positive 2. Positive 2 times negative 1 is negative 2. Negative 17 and negative 2 makes negative 19. Negative 19 and negative 1 makes positive 19, and I like where this is headed because negative 13 and 19 makes positive 6. Positive 6 times negative 1 is negative 6, and 6 and negative 6 makes 0. This is awesome. We just found one of the answers, so let's put that here. Negative 1, 0 is one of our x-intercepts. There should be 4 of them, or at least 4 values at some point in here. It may be a multiplicity factor, but we've got one of the 3. Awesome. All right. We tried 1, we got negative 1 to hit. Let's draw a new bar here and a new line here, and let's try some other values. Let's try 2. So we've got 3 again, drops down here. 3 times 2 is 6. 2 and 6 makes 8. 8 times 2 is 16. We've got a negative 3 with 19 in that. And this is going to be good too, because negative 3 times 2 is negative 6, and that's a 0. This is great. We just hit on 2 as well. So let's go up here and say 2, 0 is also one of our zeros. And the great part is we've already synthetically divided twice and got it to hit zeros both times, which means that this result down here is really 3x squared, positive 8x, and minus 3 equal to 0. Which means that now we can use quadratic methods to solve for this. We can do the quadratic formula, we can factor. I think it's factorable. Let's try to make it factorable here. There's only one factor of 3, and that's 3 and 1. There's only one factor of 3 on the back end, that's 3 and 1. And since 8 in the middle, and I know that 3 times 3 is 9, let's put the 3 here and the 1 here. Because again, 3 times 3 is 9, and this is 8 in the middle, so that's how we're going to get there. It's a positive 8, so let's put our plus here. And let's put our minus here, because again, there's a minus on the 3, which means 1's a plus and 1's a minus. If this equals 0, which it still does, then we know that 3x minus 1 equals 0, and x plus 3 equals 0, which means that x is equal to negative 3, and 3x equals positive 1, dividing by 3, x equals a third. So we just found our last two zeros here, our last two solutions, our last two x-intercepts. We've got negative 3, 0, and we've got 1/3, 0. Awesome. We are finally ready to graph this now because we've got all the steps that we need. So let's create our Cartesian coordinate system right here in the right corner. Let's first put in what we know. Well, we're not going to put in the arrows just yet, or our turning points just yet. So let's do the y-intercept first. It's at 0, positive 6. So somewhere here is 6, and we're going to have our y-intercept. There's our point. All right, let's lay in our x-intercepts next. We know we have negative 1, 0. So here's negative 1. Put a point there and call it negative 1. We're also going to have positive 2. So 1, 2. Put a dot there. We've got a negative 3. So here is negative 2, negative 3 right there. And then finally we have positive a third. So very small, right about there is a third. Again, if this is 1, that's going to be about a third there. All right, this is great. Now we can lay in our endpoints. We know that the far right goes up and the far left goes up. Well, our far right is this 2. It's the last point we have going on the right-hand side, so it has to go up like that. And the same with this negative 3. It's the far on the left hand, so it also has to go up because of the endpoints we discovered. All right, so now we ask the easy questions. How does our graph get from positive a third to positive 6 back to negative 1? Well, there's only one path that can take. And there it is. So now we have to see is where does it go rest? Well, none of our x-intercepts had a multiplicity, meaning that we're not going to see this behavior that we see over here in the higher order graphing that is going on with that. So that means we're going to have nice smooth curves here. So in other words, to connect from negative 1 to negative 3, it's probably going to be a curve that looks something like this. And the same that goes from 1, or positive a third, to 2. And there we go. Does that satisfy the turning points of 3? Let's see here. It's going down. It turns. There's one turning point. It goes up. It's going up. It's going up. It's going up. It turns. That's the second point. Going down. Down, down, down. Turns again. Goes up. That's 3 turning points. This totally satisfies the path of the graph. So great job in getting us that far. It works if you follow the steps. Follow the steps. It seems like a lot. I know. Trust me. I know. But that's why the steps are here.